In the first part of this lesson on the fundamental theorem of calculus, we talked about the relationship between the accumulation function and an antiderivative. We linked it to what's called a definite integral, and now we'll do a number of examples of what are called definite integrals. So in this integral, we're going to integrate x squared dx, but we'll be integrating it on a very small interval, on the interval from 1 to 2. Now graphically what that means is we're considering the quadratic x squared on this interval from 1 to 2, and we're trying to figure out, in one sense, what is that area under the curve in that region. And previously we've cut that up into rectangles or trapezoids and things like that, but it's the fundamental theorem of calculus that links this to more of maybe an algebraic way of doing things. So 1 and 2 are called our limits of integration. And because this is a definite integral, there will be no constant of integration, no c in our answer. We will just have a numeric value when we're done. So we know that the integral of x squared is 1/3 x cubed. And we're still going to be integrating this from our interval from 1 to 2. By the fundamental theorem of calculus, then, this is going to be equal to what we get when we substitute 2 into our new function, our big F, which is what 1/3 x cubed is. This would be big F of x, and this would be considered little f of x, although we would never write this stuff down. It's just how we're thinking about it, connecting it to the theorem. And it's always minus the lower limit of integration substituted in. So in this case, 1/3 times 1 cubed. I'm just going to continue to show my work. 2 cubed is 8, so this is going to be 8/3 minus 1/3, which is a grand total of 7/3. So at least graphically what that means is this area under the curve is exactly 7/3 square units. That's what we're talking about. It's one way of interpreting this, is area under a curve. And for our purposes, we're focusing on the process of working through a definite integral. Let's look at another example. In this case, the integral from -1 to 3 of 3x squared minus 2x minus 1 dx. So we're integrating with respect to x, that's what the dx tells us. And the integral of 3x squared is x cubed. The integral of minus 2x is x squared. And the integral of -1, or minus 1, is just minus x. And we're integrating this from -1 to 3. And when I do that, if I plug 3 in to this entire function, I'll have 3 cubed minus 3 squared minus 3, and that quantity minus 1 cubed minus 1 squared minus 1. Well, 3 cubed is 27, and 27 minus 9 is 18, and 18 minus 3 is 15, so we've got 15 minus 1 minus 1 is 0, minus 1 is -1, so 15 minus -1 is 16. Let's look at a third example of how to evaluate a definite integral. The integral from 0 to 9 of root x dx. Well, the square root of x is the same as x to the 1/2. So integrating this, I know this must have come from x to the 3/2, and since that got divided out, the original coefficient must have been 2/3. And this I'm integrating from 0 to 9. So it's always the upper limit minus the lower limit. So something to the 3/2 means the square root of that number cubed. So the square root of 9 is 3, and 3 cubed is 27, and 27 times 2/3 is 18. So when I substitute in 9, I get 18. When I substitute in 0, I get 0. So my answer is just 18. Let's look at the integral from 5 to 10 of 2 over 3x squared dx. Now, personally, I benefit from rewriting this as 2/3 x to the negative 2 power. Don't want to forget the dx. It tells me what I'm integrating. And when I integrate that, this will go back to x to the negative 1 power. And in order, negative 1 times what is 2/3? Well, negative 2/3. And this will be evaluated from 5 to 10. When I substitute in 10, 10 to the negative first is the same as 1/10. So this will be negative 2 over 30, or negative 1/15, minus, when I substitute in 5, it'll be negative 2/3 times 1/5, or negative 2/15. And altogether then, I'll end up with 1/15. And we have the integral from negative 1 to 1 of 2x minus 1 squared dx. We can do this using u substitution, or we could try to unpack the chain rule ourselves, and so I'm going to try and unpack the chain rule myself. I know that 2x minus 1 squared must have come from 2x minus 1 cubed. I also know that when I had dropped the 3 to use the power rule, it's no longer there in little f of f, so there should be a 1/3 out front. Finally, I would have multiplied by 2 in the chain rule, and that 2 got divided out. So in order for that to get divided out, this should have been 1/6. Right, so that's going through and evaluating everything, trying to unpack the chain rule in my head. And some of you can do this. If I had to use u substitution, I'll do it that way. I would say that u equals 2x minus 1. So du equals 2 dx. So 1/2 du equals dx. So by u substitution, my integral becomes negative 1 to 1 of 1/2 u squared du. Now there's some other things that need to happen if I'm going to do it this way. These limits of integration are in terms of x, but everything's in terms of u now, and that includes my limits of integration. So I'm going to need to change these. So one thing that's true is that when x is 1, then u, using what u equals 2 times x minus 1, when x is 1, then u is also 1. Well, that was convenient. And when x is negative 1, then u is negative 3. So I've got to change my limits of integration to have them also be in terms of u. Now when I integrate 1/2 u squared, well, that would have come from u cubed. It got divided out, so it would be 1/6. And I'm evaluating from negative 3 to 1. I'm going to go back to get it in terms of x, just to show you that it's the same as what we got earlier. Since u is 2x minus 1, this will become 1/6. 2x minus 1 cubed. And my limits of integration need to go back to being in terms of x, so from negative 1 to 1. Now if we evaluate this, if I substitute 1 into my function, this will be 2 minus 1, which is 1. 1 cubed is 1, and so I'll just have 1/6 minus, if I substitute negative 1 in, 2 times negative 1 is negative 2, minus 1 is negative 3. Negative 3 cubed is negative 27, so this will be negative 27 over 6. I'm going to leave it like that so I have a common denominator. And this becomes 28 over 6, which reduces to 14 thirds. One last thing to point out, I could have just evaluated it from here and not change anything back, and I'll get the same answer. If u is 1, then I'll have 1/6 minus. If u is negative 3, then that will be negative 27 over 6. And when we combine these, as we already know, we'll get 28 over 6, or take it down to 14 thirds. So what you have here are a few different things to consider if you're going to use u substitution. You could just kind of plow through the chain rule, which you guys have to keep track of a lot of different things. You can use u substitution, but must remember to change the limits of integration to be in terms of u. You can change everything back to evaluate, or you can just keep everything in terms of u, and in all cases you'll get the same answer. Looks like we'll have to add another part to this because this is getting kind of long. So in the third part on Fundamental Theorem of Calculus, we'll look at 4 more examples, and if there's time, we'll consider how to use technology to evaluate these as well.